Hi, my name is Mark Nizovich and this is my final year project of Soil Analysis Instrument Pack. My supervisor for this project was Dr. Andrew Price. The geoscience faculty requires a device that can take soil samples and measure soil pH for their ongoing research into the variability of soil chemistry. The aims and objectives of this project was to develop a prototype that could accurately take pH measurements, that could take 16 5 cubic centimetre soil samples, and would be able to fit in this orientation into the instrument bay of a rover which is currently under development. And one of the limitations was the space available was only 400 millimeters by 150 by 150. Okay, so this device has to perform two functions, the first of which is to take soil samples. This is accomplished through the use of 3/8 inch barrel nipples made from stainless steel. Materials such as copper, brass or gal will react with the soil and contaminate the samples. I found during testing that if I was to drill in a clockwise direction, that the threads would foul up, which is a problem because when it's inserted again into the carousel, it's got to go in a clockwise direction, so the soil fouling the threads became an issue. So I found if I was to rotate them in a counterclockwise direction, that didn't happen. The sample containers are driven by this 12-volt motor here and are connected through the quick coupler, which is an off-the-shelf item. The carousel itself is made from 3D printed PTEG, and all this is accomplished using the one mechanism, which is an important thing due to the space constraints that I had. However, taking soil samples isn't quite enough, so the second function this device must perform is to take instantaneous pH measurements. One of the considerations is that 41% of Australian agricultural soil ranges between 4.6 and 5.5 pH, and 15% of the soil is below 4.8 pH. Another factor was that this device has to be inserted into the ground multiple times, and there's a fair bit of force involved. During the testing phases it could range between 10 and 20 kilos. So glass membrane sensors, while very accurate, really weren't suitable for it. So I chose a dual probe sensor for several reasons, one being it's compact. The range of this sensor is 4 to 10 pH, the accuracy of it is half a pH, and the resolution is 0.1 of a pH. The next thing I'd like to talk about is the deployment system. A couple of challenges here with the overall size constraint due to the range of travel between the stow position and the ground engagement position being about 300 millimeters. So to overcome this, I employed a two-tier scissor system. The scissor itself is driven by a lead screw connected to a stepper motor. The stepper motor allowed for accurate placement of the scissor mechanism. Now servos are used to orientate the sensor and the drill motor. An important thing to note there is that the servos don't directly drive the sensor and the drill, otherwise they'll be damaged, so that's accomplished using a gear train and a pillow block system. The carousel is driven by a stepper motor also, which allows for accurate placement of it, and the whole thing is controlled by an STM32 nuclear board. So for the results, I'd just like to show you a quick video. In the video it shows the drill rotating from the upright position to the vertically down position. The drill motor starts, it's then pressed into the ground with the scissor, acquires its soil sample to the correct depth of 5 centimeters, is withdrawn, rotated 90 degrees, and you can see in the picture there that we've got a good sample. And then the pH sensor is rotated into position, it's inserted. When it reaches the correct depth of about 5 centimeters, it then would typically wait about 10 seconds, 15 seconds for a good measurement to be acquired. Other results included that the device fits the size constraint. Now the scissor successfully deployed the soil sampling system and the pH sensor in a vertical fashion. So and that's important because we want the drill and the pH sensor to be inserted as perpendicular to the soil surface as possible, and it's also important for the soil sample container exchange. Future work for this project would include serial comms with the rover, pH sensor data acquisition and then writing that to the SD card. I'd use a higher torque DC motor for driving the drill motor. I'd also serrate the cutting edge of the sample container, as during the feasibility study I tested the theory using a whole saw and it worked very well. This would allow the device to sample a wider range of soils. I'd also taper the inside of the sampling container so that it would retain drier soils better. I use a high capacity stepper motor drivers and potentially a larger stepper motor just to increase the amount of force that I can exert downwards. Again, this will just make it a more versatile device across a wider range of soil types. A system that would squirt a jet of distilled water onto the soil, pH sensor between measurements so that keeps it clean and accurate. And potentially I would look at finding a sensor that has smaller cross section in the probes, which would allow less force to be used and also would allow us to test soils that are a bit more compact than cultivated soils. So this is my project. This is a soil analysis instrument pack. Hope you enjoy the presentation.